one of the presently prominent physicists, Michio Kaku, has discussed his evaluation with respect to the discoveries made by the James Webb Space Telescope, JWST. Kaku, renowned for his remarkable contributions to the fields of physics, has recently affirmed that the JWST has found 6 immense cosmic systems that scientists previously thought couldn't exist. These assessments have the potential to open up new perspectives in our understanding of the universe. Therefore, it is fascinating and worth watching out for these changes. Kaku is a unique figure in the scientific field. A physicist of American and Japanese heritage, he is considered a master in both traditional exploratory physics and quantum mechanics. Unlike some more moderate and skeptical scientists, Kaku has embraced the surprising implications of the JWST mission. We are pleased that this distinguished scientist has chosen to end his silence and transparently share what can no longer be denied. The excitement and engagement in Kaku's tone are clear in his comments on the discoveries made by the JWST, indicating that this has been a highlight of his interest. Join us as we explore the ramifications of Michio Kaku's revelation of these 6 enormous cosmic systems. Kaku is a scientist who has always been able to think creatively about new theories throughout his life. He understands that Einstein's theories of relativity and Newton's laws are insufficient to capture the full complexity of the universe. Kaku believes that the discoveries from the JWST can significantly improve the scientific field, although many of his colleagues have not been able to embrace this view. This situation is causing concern and sleeplessness among defenders and adversaries of quantum mechanics, but it merely incites laughter from Kaku. The JWST has uncovered revelations of 6 enormous worlds tracing back to the earliest epochs of the universe. Each of these cosmic systems contains more stars than our own, despite having formed just a short time after the Big Bang. The group of cosmologists who made the discovery has named these exceptional systems universe breakers, as their existence would fundamentally alter our understanding of the universe. The current theory of the Big Bang suggests that the universe was chaotic after the initial event, with the first solid objects requiring centuries to form. It was believed that complex structures like galaxies should have developed much later. However, some of the newly found systems outperform the Milky Way in size, and their colossal radiance indicates that they were likely forming many new stars each year, while our galaxy forms stars only intermittently. It remains unclear exactly when the first galaxies formed. Until recently, researchers could only assume that initially, there may have been single stars or small gatherings that eventually came together to form progressively larger structures, leading to the development of dwarf galaxies. This discovery raises the question of whether the universe is much older than previously accepted or whether complex structures formed significantly earlier than thought. This situation poses a challenge for mainstream science, which struggles to reconcile these findings with existing models. Furthermore, some areas of physics have strongly rejected this discovery, addressing possible errors in age calculations. Kaku is aware of this contention and has remarked that many old and misleading hypotheses persist due to the prominence of certain scientists. Many of these speculations have been disproven when vital research revealed their inaccuracies. In fact, on Earth, we have practically no knowledge of the genuine beginnings of the universe. The Big Bang hypothesis was proposed in 1927 based on observations of the universe's development, leading to the conclusion that the universe began from a singular point and has been expanding ever since. At that time, it was challenging for people to imagine a universe with both a start and an end. The possibility of an eternal universe was beyond human imagination. Even today, researchers still face difficulties in comprehending it. However, it is critical to re-examine these possible outcomes. These new perceptions do not align with what researchers have relied on for quite some time regarding the Big Bang hypothesis. Yet, science has shown repeatedly that reassessment and receptiveness to groundbreaking ideas are significant parts of the scientific process, just as much as the affirmation of specific hypotheses and observations. When Einstein was a child, it was believed that the stars and planets were fixed in place, occupying a defined space. However, we now understand that everything in the universe is in motion. Planets orbit stars, stars move within galaxies at numerous kilometers per second, and entire galaxies rapidly traverse the universe, the fate of which we cannot yet predict. Today, researchers are challenged to accept uncomfortable insights, recognizing that hypotheses are not simply guesses or essential facts until thoroughly tested and confirmed by precise observations. The idea of the Big Bang arose from the acknowledgement that galaxies are moving away from one another, a phenomenon described by Hubble's law, which proposed that the universe was expanding. For some time, various pieces of evidence, such as astronomical microwave background radiation and the redshift of light from distant galaxies, seemed to support this hypothesis. However, it is essential to remember that in the past, people who believed the Earth was flat also had similar proof for their beliefs until events or technological advancements provided a clearer picture. Currently, we find ourselves in a comparable situation. Researchers expected the JWST to affirm the assumptions associated with the Big Bang, yet instead, they discovered 6 systems that appeared incomprehensible. This serves as a reminder that science is continually evolving, and researchers must remain open to new discoveries and rethink existing hypotheses in light of available evidence. Redshift, a tool used to determine distances in the universe, refers to the adjustment of the color of light as the light source and the observer move relative to one another. To understand this, one can imagine watching a vehicle coming towards you. As it approaches, the engine sound gets louder. Once it passes, the sound changes. The same principle applies to light. When a distant star moves towards us, the light shifts towards blue tones, and when it moves away, the light shifts towards redder shades. This phenomenon, known as redshift, has allowed physicists to convert redshift values into velocities and distances for measuring cosmic amounts. However, small errors in these measurements can have significant implications. The methods previously used for these measurements are now under review, and the results that specialists will arrive at concerning the latest discoveries about our universe are intriguing. It is pivotal to consider whether these outcomes are genuinely based on measurement errors or if some specialists are simply denying the facts. This question requires intensive assessment and careful review of the data and methods used in the research. As scientific inquiry progresses, discoveries made by instruments like the James Webb Space Telescope frequently challenge our assumptions about the universe. The new revelation of 6 massive cosmic systems, tracing back to the early epochs of the universe, is one such example. These systems, which defy conventional hypotheses of universe formation, raise significant questions about the timeline and components associated with the development of large structures. The JWST, equipped with cutting-edge technologies, enables astronomers to peer deeper into space and observe with remarkable clarity. Its ability to detect light from the distant reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive worlds challenges existing models, which predict that such large structures should have formed much later in the universe's history. The ramifications of these revelations extend beyond astronomy and into fundamental physics, compelling scientists to reevaluate established theories about the early universe, including the theory of its origin. This theory posits that the universe began from a single point and has been expanding ever since. While observational evidence such as the vast microwave background radiation and the redshift of distant galaxies initially supported this hypothesis, the discovery of galaxies appearing too developed for their age complicates this narrative. Michio Kaku, known for his ability to connect complex scientific ideas with public understanding, recognizes the pivotal potential of the JWST discoveries. Unlike some of his more skeptical colleagues, Kaku embraces the notion that momentous observations should provoke modifications in scientific thinking. He emphasizes the importance of experimental evidence in shaping our understanding of the universe, highlighting that theories must continuously evolve to accommodate new data. The debate ignited by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, advocates argue that the discovery of early massive galaxies suggests a longer timeline for cosmic development than previously thought, challenging the traditional view that galaxies evolve gradually through mergers and steady growth. On the other hand, skeptics caution against hastily discarding established models based on limited observational data, advocating for a cautious approach that considers potential errors in data interpretation. Redshift, observed in the light emitted by distant galaxies, plays a critical role in these significant investigations. As galaxies move away from Earth, the light they emit shifts towards longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy's spectrum, astronomers can infer its distance and speed relative to our galaxy. This information is essential for constructing models of cosmic evolution and understanding the distribution of galaxies in the universe. The JWST's ability to detect faint infrared signals allows it to observe galaxies otherwise obscured by dust and gas in the early universe, a period known as the cosmic dawn. By analyzing the light emitted by these distant galaxies, astronomers can trace the early universe's chemical composition and gain insights into the processes that drove the formation of the first stars and galaxies. Moreover, beyond its cosmic implications, the discovery of these early massive galaxies raises philosophical questions about scientific advancement and human understanding over time. Scientific paradigms have shifted in response to new discoveries. What once seemed impossible eventually becomes accepted as new evidence arises. This iterative process of theory, observation, and revision is fundamental to the advancement of knowledge across all scientific disciplines. The concept of a paradigm shift, as articulated by philosopher Thomas Kuhn, describes the profound change that occurs when anomalies in existing theories prompt a major reassessment of scientific principles. The discovery of early massive galaxies compels astronomers to reevaluate their understanding of cosmic evolution and the processes leading to the galaxies we observe today. It underscores the importance of remaining open to revolutionary ideas and revising theories based on experimental evidence. Cosmologists and astrophysicists are also grappling with the implications of these discoveries for dark matter and dark energy theories. If galaxies formed more rapidly than current models suggest, this may impact our understanding of the role dark matter plays in cosmic structure formation. These fundamental questions challenge existing frameworks and invite new inquiries into the properties and behaviors of the universe. As Michio Kaku and other scientists advocate for embracing these extraordinary findings, they highlight the significance of scientific curiosity and exploration. The JWST's discoveries represent an exciting frontier in understanding the cosmos, prompting scientists and the public alike to rethink long-held beliefs about the universe's history. As we continue to probe deeper into the universe's mysteries, it is essential to remain adaptable and receptive to new ideas that challenge our understanding of the cosmos. In conclusion, the discoveries made by the James Webb Space Telescope offer a fascinating glimpse into the early universe, revealing 6 massive cosmic systems that defy previous assumptions about galaxy formation. These revelations have profound implications for our understanding of cosmic evolution and compel scientists to reevaluate established theories in light of new evidence. As we navigate these new landscapes of knowledge, it is crucial to embrace curiosity, remain open to innovation, and recognize that science is an ever-evolving pursuit of understanding the universe and our place within it. The revelations brought forth by the James Webb Space Telescope, JWST, continue to capture the imagination of scientists and enthusiasts alike. With its advanced technology, the JWST is not only redefining our understanding of cosmic structures but also challenging the very fabric of theoretical astrophysics. The telescope's ability to capture high-resolution images in the infrared spectrum allows astronomers to investigate celestial bodies that were previously hidden behind dense clouds of gas and dust. As researchers delve deeper into the data collected by the JWST, they are uncovering a myriad of phenomena that were once deemed implausible. For instance, the detection of unusually bright galaxies, which appear to have formed within mere hundreds of millions of years after the Big Bang, suggests that the processes governing galaxy formation are more complex than previously understood. These discoveries necessitate a rethinking of not only galaxy evolution but also the conditions present in the early universe. Moreover, the JWST has prompted discussions about the possibility of different evolutionary paths for galaxies. It raises the intriguing prospect that some galaxies might have formed through mechanisms that do not conform to the established models. This could involve rapid star formation rates or unique interactions with their surroundings, thus leading to the emergence of massive galaxies earlier than anticipated. Additionally, the implications of these findings extend into the realm of exoplanet research. The data gathered by the JWST can be used to analyze the atmospheres of distant planets, potentially revealing the presence of water vapor, organic compounds, and other indicators of habitability. This could significantly enhance our understanding of where life might exist beyond our solar system. Furthermore, The JWST's findings may catalyze new technologies and methodologies in observational astronomy. As scientists grapple with interpreting complex datasets, interdisciplinary collaborations will likely become more prominent. Astrophysicists, computer scientists, and data analysts will unite to develop algorithms that can sift through vast amounts of information, thereby facilitating the identification of patterns and anomalies. In essence, the JWST is not just a tool for observing the universe. It represents a paradigm shift in how we approach astrophysics. By challenging long-held beliefs and inviting new questions, it ensures that the journey of discovery will continue, fueling human curiosity and expanding our comprehension of the cosmos. As we stand on the brink of a new era in space exploration, the potential for groundbreaking insights remains boundless.